Well, hi and welcome to my shop, and thanks so much for joining me here. It's April, May 10th. Been a couple days since I've posted a video. Yesterday I was in here, I did a complete alignment on this radio. Videoed the whole thing, but then decided, you know, it didn't go well enough to put on a video. Too much circuitous thinking and all kinds of craziness went on. But I did manage to get all the way through the alignment. And the result was pretty good on all bands but the highest band. So I thought today, okay, let's do it again, because generally I accept that the first time through an alignment with a radio can be written off just to education, just to learning all the little ins and outs of what might be up. So that's okay. Didn't come out perfect, but I have a chance today to go over it again. So I thought, well, why don't I spice it up a little bit, and we'll make an attempt at doing a sweep alignment of the IF. Previously I aligned it with a single frequency. Seemed to go fine. I don't think there was any problems with it, but why not have some fun and do a sweep alignment? So as usual, I like curiosities that happen in my shop that I look at and go, what the heck is happening there? You can see my scope with some blips on it. We're going to look at those blips in a minute. Let me just explain what I'm doing here before we do that. So the radio's on and operating. That's the sound of the sweep generator. That's this guy going here. And it's sweeping between 420 kilohertz and so 420 to 480. And in between there is 455. So look at it sweeping again. As long as I keep the volume down on the radio, we don't have to listen to it. The sweep is being put up on the scope. Now the way the scope does this, the scope and the sweep generator has a sweep output. That's this cable here. That's going over to this spot, and that's what's causing the sweep on the scope. It's not the scope itself. It has a special setting here called XY. So the sweep is coming from the sweep generator, and that's to coordinate the sweep position with the frequency that the sweep generator is operating at, because it's a rising frequency, right? It's going from, what was it, 420 to 480. It's doing that in 10 milliseconds according to the machine. So every 10 milliseconds you get a sweep going by, and the scope displays it up here. What exactly have I got my scope hooked up to then? Because the vertical input is connected basically to the output of the detector in the radio. You can kind of see the connection here. The scope lead going in. That can disturb the radio a little bit, but I thought, well, we'll just start this way. Let's see what goes on. So what I would expect to see is basically a line with a dip like this, and then onwards. And this would be the response curve of the IF. This shape here. And this shape is on there. Let me just flip to a different camera here. So now, first of all, my scope still has some problems. So you see how this is stretching out a little bit? It's kind of pulling to the side. I think it's from a dirty switches up here. So just kind of ignore that. And look at my ghostly face there too. Isn't that kind of weird? It's very weird. This is the response of the radio. This curvy part here. So if I put a little volume on, okay, now if I increase the sweep amplitude, you can see that happening. Okay, that's perfectly normal. My intention was to measure the frequency of this point, observe the shape of this curve, fiddle with the alignment a little bit and see if I can make it any better. What are those other blips? What are those other things that are in there? That's a really interesting question. So I'm talking about this. You repeat it. It looks like they're exactly the same distance apart. What the heck is that? And is it of any consequence? Is it because of the radio? Is it because of the way I have things set up here? Or is it something to do with something not really related to the radio? Or is it indicating something about this radio that's worth knowing? And I got no answers to any of those questions. So I'm just looking at it myself now, looking at the shape there. Well, I think I'm going to drink a little coffee and ponder the situation. Then I'm going to measure this frequency and find out if it's 455 or not. And do a little alignment stuff. And maybe somewhere along the line, these dips will make themselves known. Maybe. Okay, have a cup of coffee. Those things are still there. So I'm not doing this maybe as appropriately as I could. I'm feeding the signal generator signal into the antenna, whereas I could probably be feeding it more directly into a tube grid. Maybe that would make a difference, particularly if I focus on just the second IF. Why don't we try that? Right now it's going through the whole radio basically to produce that, and I can restrict the sweep signal to just going through the IF, or at least entering the IF. I think that might be a good idea. Okay, I'm going to stop and figure that out. Oh, one thing to show here. Just 1 second. Let's just take a look at this. If I tune the radio, just turning the tuning knob here. What's going on? Let's listen to this. What do we hear? You hear those things? Oh my gosh. Let me change things a little bit here. Okay, turn down the volume here, and you can watch me tune this thing and see what happens. What is going on? Was another effect. If you watch the actual response spot, let me turn this up a little bit here. If you watch the actual response spot, it's changing too as I tune the radio. There's just so many things going on. So what exactly are we seeing here? Now I've got another signal generator connected right now. It's set to I can't read the number. 450, very close to 455. And what that'll do is it'll put a squiggle into the, it should put a squiggle in here. You see how squiggled it up it is? Let's just see if that isn't that actual signal generator. So I'm just going to vary the frequency of what this would be called the marker generator. Earlier on when I was setting this up, I thought, no, you can't even see it. And no, you can't even see it. So, don't know so much I don't know. Holy smokes. Okay. Can't let that get in the way though. Actually, that seems to be the theme in society these days. No matter how stupid you are, get going. Open your mouth. Go march somewhere. Right, so I'm going to inject these signals somewhere other than into the antenna. I want to put it into the grid of the mixer tube. I think that's really my only option. And I could also stop the oscillator if I wanted to, the local oscillator. But so let's see, is this got to be pin number? I can't read it on the schematic, for crying out loud. Okay, let me get this set up. I'm just going to transfer the input point for the test signals from the antenna to the grid of the mixer tube, the first tube in the radio, really. Okay. Oh my gosh, I can't turn down the volume any lower. I have to get rid of the speaker. Okay, well there we are. That's a far better looking kind of signal to work with, no doubt about it. So what I've done is I've simply moved the signal injection point past the few front end coils and stuff like that right onto the stator plates of the tuning side of the capacitor, the tuning capacitor. And so I'm feeding it in a loop. So, and the result of that is I'm feeding it directly to the grid of the mixer tube, the signal grid, not the oscillator grid. The oscillator is still running in this radio. I've only hooked up the sweep generator. Okay. Oh my gosh. Hey, well that's interesting. Hook it up to the antenna, get some strange effects. Not too surprising, eh? Hook it up right on the grid, eliminate some of the strange effects. I'm talking about those peaks that were appearing there, which I still have no idea what they were. So now this is the marker generator here, which I'm also going to connect to the same place on here. It happens to be extremely convenient in this radio. As soon as my camera comes back to life here. Jeepers creepers. I mean, you have to tickle them all the time to make them work. The connection is right to a screw sticking out of the top of the capacitor, which is the support for the stator plates. Okay, so we're doing this to the B minus connection. Here we go. We'll just put this on here. What happens? Anything happening? So it's reducing the display on the scope ever so slightly. That's not to be too surprised. Okay, now we're going to introduce the next signal, and we're looking for a squiggle to come traveling through here. I'm just going to move the camera out of my way while I do this, because you can see the scope no matter what. We're at 450 with a fairly low signal. What do we see? We see nothing. Okay, this usually requires a pretty strong, oh now I'm seeing something. There we go. So you see the squiggle traveling through, and you can hear it. Let me turn this up a little bit. Okay, so I simply center the squiggle. In a better operation, that squiggle is a pip. But in this case, it's just a squiggle. Put it right on the bottom, and then we read the magic frequency. 455. It's right on the money. This is this number, this actual frequency would be 456, with this saying 455. So it's just a touch high, but not enough to worry too much about. But I did notice something else about the wave shape. Let me put the whole thing on the screen here and turn. I'm going to move the marker away. I'm going to increase the input. Well, I don't see it now. So what I had noticed earlier, which was just a figment, was this shape wasn't all that smooth and balanced here. It had a funny kink right in the side. Oh, that indicates one of the IF cans is a little out. I don't see it now. Let me tune the radio around. This shouldn't make a difference, but that's only what I think. Change in the oh, I wonder if the kink was because I had the other signal generator sitting there, but it wasn't connected. Doesn't seem to be any kink there now. Well, we've gone this far. I might as well try adjusting the IF cans, and let me just see what if I can do anything to improve that, bearing in mind it's right in the right frequency. So I'm going to set this, I'm just going to move it using the scope so it's right on the center line so I can keep track of it. Because we know the center line is 455. And I'm going to try adjusting these these guys a little bit, but I can't imagine I'm going to improve it. Here we go. First one. You can actually see where the peak is running. Kind of just judge that it's over there. You listen to the sound too. Just look for it to be nice and balanced. Okay, didn't get anywhere with that. Try this one. Same sort of thing. You can kind of see where the... That's an unusual effect, isn't it? Right there. I don't think that got anywhere. Next two. Sometimes when you do it with a single frequency, when you do the alignment with a single frequency, you can end up with a misshapen response curve and not know it until you do something like this. But that's not the case here. All these are bang on, so it made no difference. But let's bring in that other signal generator just to double check that we are at. It's right there. 458 on the meter. Let me turn up a little higher here. Make it more apparent. I would say that's the spot right there. 457. 457. Okay, let's do this. We'll set the signal generator to 455, which actual on my counter would be 454. Okay. And it seems to me it's, I wish I was watching more closely. It looks like it's here. Can't watch two things at once, which is one of the problems. So I think it's there. I'm going to move the display here. So I think that's 455 there, where the center line is. I'm going to try to push that whole curve over. So it's a really very minimal bearing on the operation of the radio, except for accuracy of the tuning. That's what I think. So we'll try this one. Hard to tell. I think we'll probably do these a few times to get them all to agree. Just keep working them over. In some ways, this is more difficult to do, what I'm trying to do here, than the single frequency approach. Got this shape thing to deal with, as opposed to just an indicating meter reading. Looks pretty good now. That last screw seemed to do everything. So looking at the shape, nice and balanced. It's really kind of a question of symmetry in the look of the response curve. Okay, there it is. I beat that to death. So, IF definitely aligned. Very good. Okay, the next challenge with this radio is to deal with the image response on the high frequency band. That's the shortwave band that goes from 13 all the way up to 32 megahertz. That's really high for a radio like this. And there's an issue with shortwave radios that go to these kinds of high frequencies, but still have low frequency IF frequencies. The low frequency IF frequency in here is 455 kilohertz. So I'm going to try to explain what the issue is with, is a local oscillator above the tuned frequency or should it be below the tuned frequency? And I'm going to talk a little bit about image frequencies, image signals and stuff like that. So if you know all this stuff, then just ignore everything I'm going to say, because it's probably not 100% correct anyway. Let's say you're tuning around you want to tune a signal in the broadcast band at 1 megahertz. So I'll try 1 megahertz signal there. That's at 1 megahertz. That's what you want to listen to. So in a radio like this, by tuning, you actually are introducing and changing the frequency of a local oscillator, another oscillator. So I'm going to draw it here. There's a reason why I'm drawing it here. So this would be the local oscillator in the radio, and when you tune the radio, you change this frequency around. It goes up and down. Now the radio itself really is only, bulk of the radio is only receptive to 455 kilohertz, which I just made sure of with the checking of the IF frequency. 5 kilohertz. So if the signal being presented to the IF is not 455 kilohertz, it's not going through the radio. That's the whole trick of these things. So how do you get 1 megahertz signal to be 455? You convert it using a trick, and the trick is if you take these two signals, and I'm going to very carefully pick a frequency here, 1,455 kilohertz, 1455. So local oscillator is running at 1455. The radio is trying to tune a megahertz. The radio can only hear stuff at 455 kilohertz. What's happening? These things are going to get mixed together in the radio, in the mixer tube in particular. And the result of mixing two frequencies together is you get the sum of the two and the difference of the two. You get more signals, oddly enough. So you get the sum of the two. So if you add these two together, you get 2.4. That's way 2.455. That's far, far, far away from there. But if you look at the difference between these two, because I was clever and I selected it very carefully, the difference is 455 kilohertz. And if you can present this to the IF and the rest of the radio, it's going to go through and come out of your speaker. Well, what if you want to tune this signal? Well, you just lower the local oscillator frequency down by tuning the radio until it is 455. So what's really happening here is all the signals that are on here, noise, radio stations, everything under the sun, is being multiplied, that's not quite the right word, it's being affected by this local oscillator being mixed in with it. And you're not just getting the target frequency being presented, you're getting everything. The whole AM band is being converted by this local oscillator, and it's all being presented to the front end of the IF. But the only thing that can go through is anything at 455. Now what's the problem with this? Well, the problem is, what happens if there's another station in here 455 kilohertz above this? So if we have 455, what do we get? We get 910, so it would be 1.910. I hope I got the arithmetic right, but if I don't, it doesn't really matter. I'm sure you're smart enough to figure it out. What if there's a signal there? Notice this particular example, this is outside the AM band, but we all know that there's all kinds of noise down in these low frequencies. So there's a good chance there's a strong signal at this frequency, just noise, just some kind of digital device making noise, and there it is. Well, this will also go through the mixer tube along with the local oscillator and get mixed. And if it produces a 455, if it happens to be 455 kilohertz away, bingo, it's going to come out the speaker. This is called the image. And why? Well, I think if you think of this like a mirror, it's a little like a mirror image. I think that's why they use the word image. Very confusing term for me for the longest time, trying to figure out what are they talking about here. So, you know, in this example, 455 kilohertz is a large portion of 1 megahertz. So, mixing these things around, they're getting pushed quite a ways away from 455. Another issue here is the front-end tuning of the radio. So if you have the radio tuned for 1 megahertz, there is a response curve which will look something like this in the radio. So what's happening is the signal, the image signal out here, is being suppressed by the front-end tuning. Sometimes that just amounts to the loop antenna and not much more. Other times there's a whole tube and a whole stage to try to sharpen this as much as possible. So here in the AM band, none of this is terribly critical because of this tuning, because of the ratio of the frequencies of the IF and the frequencies you're actually tuning. It's pretty easy to suppress the images, or the image should it be there. Now if there's nothing here, there's no image. There's no deal. When you're listening to the radio and you tune to 1 megahertz, and all you hear is a pile of crappy noise, you might think, wow, there's a noise signal at 1 megahertz. But there could be a big blaster up here at the image frequency, because a lot of the noises in my house anyway are way more powerful than the stations I'm trying to tune. And if this thing were strong enough, even though it's suppressed, it won't be suppressed enough. And some of this is going to come through. How would I ever know that when I'm tuned here, I'm actually hearing something from up here? Especially if this is noise, like you know, buzzing or whatever the kind of noise. You don't. You can't tell when you're tuning the radio. It just sounds like another thing coming in. You don't know. Maybe you're tuning in a station at 1 megahertz and the station is there, but you hear noise on top of it, or interference on top of it, or a heterodyne in the radio, an audio heterodyne, like a whistle. It could be coming from up here, particularly if this isn't very good. A lot of cheaper radios, this is not very good. This is based on nothing more than the tuned circuit of a loop antenna and a capacitor. There's nothing more. This just producing this. As I mentioned, other radios, they stick a tube in there. They have tuned circuits ahead of it, tuned circuits after it. Every time you add in a tuned circuit, you sharpen this more and more, and you get deeper and deeper down here. You get more and more image suppression going on. So for instance, my Hammerland SP600 military radio has 2 RF tubes in the front end before you get to the mixer stage, and that sharpens this up like crazy, like this. So what are the chances you're going to hear an image in a radio like that? Really low, very low. Even if it's you're listening to the weak station here and there's a big whopper power guy up here. You get enough front end and you're going to quiet all that down. That's the difference between a good radio and a bad radio. It's one of the differences. The whole picture changes when you start dealing with 30 megahertz. At 30 megahertz, okay, 455 kilohertz is not much of 30. So in this diagram, instead of showing these, I could do this in 2 ways, but I'm going to do it this way. I'm going to leave the curves looking like this, but the whole thing is shrunk down. So now the image is not sitting way out here because of the percentages of the frequency. The image is actually sitting right in here. Like this might be 30 megahertz, and 30 plus 455 plus 455, so in other words 910 to get you out to where the image might be, assuming the local oscillator is here. The image could be here, an image frequency. And look, there's hardly any suppression from this front end curve. It's not way out here, it's way up here. In fact, the suppression is really poor. In this radio, they actually give statistics for this. Grab them and we'll take a look at it. Different radios provide different information. This one, surprisingly enough, provides some information about, if I can find it, about this image problem. So here we are. Image ratio is what they're calling it. So they're providing you information in the form of a ratio. They're saying at 30 megahertz, the image ratio is 2.7 to 1. What are they talking about? So I think if you took, you would need, I think, an image signal 2.7 times greater than the target signal for it to sound the same, to be unrecognizable, that you're actually hearing an image coming through as opposed to the frequency you're actually tuned to. I think that's what that says. 2.7. Well, that's not an awful lot. Like if you're listening to weak shortwave signals, you could easily have one that's 2.7 times stronger, and maybe it's sitting on the image frequency location, and that's what you're actually hearing in the radio. Very hard to separate this out when you're just tuning the radio and playing around with it. As you go down in frequency, the ratio gets better. So it's 6 to 1 on the 14 megacycles. That's in the top of the next band down. 10 to 1 on the next band, and down in the broadcast band, the one I was using in my example, it's 35 to 1. So if there's an image signal, it has to be 35 times stronger than the signal you're listening to for you to hear it as if it's the same as that signal. For it to really, 35, that's a lot. But not on 30 megahertz. 2.7 is next to nothing. So what radio manufacturers do with a better radio, and going back to my Hammerland again, the way it deals with this problem on the higher bands is it converts the signal using a higher IF frequency. This stretches everything out, puts the images way out where the normal tuning suppression of the front end of the radio can suppress it, and goodbye to the images. So on my military radio, when I tune to these higher bands, the radio changes from using 455 as the IF frequency to 10.7. I believe it's 10.7, same as an FM radio. Nothing to do with FM, it's just the frequency they picked. But in fact what they do is they convert it twice. So it's called a double conversion radio. It has 2 IF frequencies in it. It uses a higher IF frequency for the higher bands in order to spread out the image distance, if you like, and enable it to be suppressed. And then it converts that to 455. It actually converts the signal twice in a dual or double conversion radio. Okay, so there's my explanation. Now, there's an issue with this right away. The issue is, what did I do with pieces of paper? I just drew stuff on. And the answer is right here. Okay, so we're just going a little bit further with this to explain the issue with this radio now. In fact, let's not use that diagram. It's too marked up. So here we are in the 30 megahertz band. Okay, and then we'll call this 25 megahertz. 25 megahertz. Now, so okay, 455 kilohertz away. So we would go. Where should the local oscillator be to tune in 25 megahertz? Well, it should be 25.455. So it should be here. But couldn't it be here? Couldn't the local oscillator be here? And that would be 455 below. So that would be 24 point, whatever. 24 and whatever the arithmetic works out to. Couldn't it be there? And the answer is yes, it could be there. You could design a radio with a local oscillator running below the target frequency or above. It's your choice as an engineer designing the radio, which way you want it to go. There might be some reasons that I'm not aware of, I'm sure there are, why it might be preferable from a designing point of view to have it below or have it above. Quite commonly, it's above on the lower bands. On this high band, you never know what they've done with the radio. That's been my experience. It could be lower, it could be higher, and very often in the radio information, they will say something. Somewhere in the radio information it will say local oscillator above on top band or something like that. There's nothing in here that says anything about anything. So yesterday I did do the alignment on this radio. After the IF, the first thing is the band I'm talking about now, the 30 megahertz band. And I did all this stuff you're seeing me do now. analyzing it, thinking about it, experimenting a little bit, and deciding that the local oscillator must be above. That was my conclusion, largely based on the fact that it was above to start with. So I left it there. After I did all the alignment of all the bands and everything at the end of my session yesterday, when I checked the 30 megahertz band, it looked to me like it was 1 megahertz out, which kind of suggests I got it aligned incorrectly. I put the local oscillator on the wrong side of the intended frequency. That's the first thing we're going to find out now. Is that really true? Or did I get it right? So we want to put in, I want to use this single frequency generator here. Put the signal into the antenna. I'm just going to hook it up here. Just give me a moment. Put in a signal and we're going to tune it. Now how do you tell? You look for the image, or you present the radio with an image frequency based on everything, and see what comes out of the speaker. And if it's louder, if the image seems louder, you've done it wrong. That's kind of how, that's how I understand it. We're going to go up near the top, where the problem gets worse and worse as you go up in frequency. So we got it on 30 megahertz. I'm liable to never ever attempt to tune this radio to 30 megahertz. It's on 30. What do we hear when I tune the signal generator up to 30? Here we go. Okay. 13. Here we go. That's pretty interesting right there. 14.6. That's another whole thing about these radios that I won't go into. My signal generator is probably putting out a harmonic. That's probably why that was heard. Let me turn down the signal strength and head up to 30. Okay, so there's one signal being received at 28.5. It's a louder signal being received at 29. I gotta turn this down a little bit here. 29.3. Nobody's at 30. It says something about how well I aligned this radio yesterday. One of these should be 30, shouldn't it? So I was quite dissatisfied when I did exactly this at the end of the day yesterday and got exactly what I got now. So something's not right. Either I just haven't got it aligned. In the normal way, it's a little out of alignment, or I've got the local oscillator on the wrong side. The stronger signal was certainly this 29 one. Let's hear that again. Well, I think the name of the game is to adjust the local oscillator until that stronger signal is at 30. Okay, I'm going to do that. We need to hook up this to the speaker. Speaker wires. Things happen all the time. Now I have to identify which adjustment is which back here. So you can see all these capacitors here. And my anti-bounce camera device has fallen out. Let me put it back in. It's one of these. And the one it is. So I'm looking at the sheet here. The oscillator trimmer is number 12. Number 12 is on the strip of 4. This thing actually looks like that. We pick 12 is the first one. This is 12. This is 12. So I'm going to adjust that and try to get this radio to receive 30 at 30. Are we really tuned to 30? Yeah. And I'm going to use this screwdriver. So what we want to do is set the frequency just a little high in the direction we want to go. It turned up here. That's what I'll do. So what we want to do is figure out which way to turn the screw first. The screwdriver's really interfering. In this case, I'm trying with a metal screwdriver first. Yeah, this is also interfering. Okay, so I had a hard time turning these screws with my plastic screwdriver, but we're going to give it a go. Oh, you know what it is? It's just my hand coming up. Very sensitive. Yeah, we're in a high frequency deal here. Okay, which way to make it louder? Apparently not that way. That way. Okay, went right by. Let's turn this back down. It's too loud. Okay, further to go. Go a little further. Okay, we went overboard, so let me put this now where it needs to be. 30. Get this on it. Barely moving the screw here. I went right by. Yeah. So those plastic tools. I've got to do this with a big honking screwdriver. Let's see if we can do it. Where are we? Way off still. It's a fraction of a turn on this screwdriver. That's pretty close. Let's call it a day at that point. Now, we should be able to dial in an image with the signal generator. The local oscillator, I'm pretty sure, is below. So we got to go down from 30 down to 29. Would it be 2990? 2990? 29,090. Okay, that's my calculation. Let's see if it's really there. Okay, so it's right there. Seem louder? Anybody get the impression that's louder? Let's turn down the volume. A little over 4. Under 4. It's remotely possible it's due to other alignment issues, but I don't think so. So there is a trimmer, and that's number 8. So looking at this, number 8. Number 8 is. Am I sure that's the right one? Number 8. Mixer trimmer. This. may not be this is where I may have made a mistake yesterday. Let's try this. This shouldn't change the tuning, it should just make it stronger or weaker. Oh my gosh. That's tuning the radio for sure. Is it? Let me turn it off. And then can we tune it in? Yeah. This says trimmer, it doesn't say oscillator. Mixer trimmer. Number 8. Is there another one in there? I'm doing the wrong one. Is that definitely 8? 1, 2, 3, 4, 5, 6, 7, 8, right across the top. They're numbered. That's got to be it. So I think this is where the rubber would meet the rubber meets the road. Where if I got the local oscillator on the wrong side of things, you may not be able to get a good response by tuning in the next adjustment. But this really seems to be acting like an oscillator here. Oh my gosh, it's noon already. It's pretty busy this morning, first thing. So I got in here a little late today. Where'd it go? Where did it all go? What all has happened here? Still there. That's right on 30. Slight touch on the tuning knob and you've gone 200 kilohertz. So is this an oscillator adjustment? Something microphonic in this radio. So we're not at 30. We're not at 30 yet. What happened? Let's go find 30. What happened? This is what happened to me yesterday. I went nuts in here. Okay, so we're setting this to 30. Close enough anyway. Back down to the real oscillator adjustment. We need to do something else. You just can't do it with these plastic tools because even a little bit of spring tension in the plastic and then this is throwing it off. That's not bad. I got something. The radio is producing 30 megahertz. Yeah, the other thing I got to do, we got to look at where that local oscillator really is. So let me do that. Okay, we're looking at the SDR, and what we see on the SDR, this is the local oscillator blasting away over here. And what I'm checking for is the 30 megahertz signal I believe I'm sending over there. So I'm going to increase the signal strength, make it visible on the SDR. Okay, I'm going to vary the signal generator to, again, make it visible on the SDR. There it is. Okay, so the sound you're hearing is coming through the other radio. So my SDR is quite accurate. I'm going to set this on the red line. So on my frequency generator, it's 29.990. It's actually a little different than what I thought. I guess the error gets greater in my signal generator as I go. So now we know there's a 30 megahertz signal. We hear it coming from the radio. This is the local oscillator. Where is it set? Okay, let's just get the red line right on. It's set to 29,562. So it's below 30. That doesn't quite work out with 455, does it? If you add 455 to 29,562, you get 30, you get over 30. How can that possibly be? The radio's not actually tuned. Let's tune it. Yeah, that's just the problem. Hair trigger tuning. That's better tuning there. Now, go here. So you see what I was doing was changing the local oscillator frequency. So we got 545. If I have to click this up one, it's right on the money now. 545. You add 455 to that, you get 30. Perfect. Perfect. Everything is set now for 30. What am I doing? Somebody help me. I've been in here too long. So we want to go down. We want to change the signal generator from 30 to 29, whatever it was, and measure the signal strength again. So we're listening to something here because I retuned the trimmer. We'll go down and find the image. Oh boy, can you tell the difference? Can anybody tell the difference between those two? You should be able to tell the difference. Let me switch cameras here. Should be able to tell the difference. So this is the audio output. Highest reading is looks like 3.3, and that's at 29. I'll go up to 30. It's really exactly the same. I think I got to do this again. This time put the local oscillator above and see what kind of results we get here when we do the image rejection thing. So local oscillator above. So if we tune to 30, the local oscillator should be, if we tune the radio to 30, the local oscillator should be 3455. Okay, so let's look at the SDR and I'll try to get there. In fact, I'm going to stop and put it right on the screen here. Okay, so we want the local oscillator to be above, and we want it to be at 3455. So I'm going to adjust the trimmer and try to move it up to 30. I'm going to mark it on here. 3455. So it'll be 3455, right where this red line is. So I'm going to move this all the way to here. When I get here, we should hear the station. We should hear the tone again. Man, it should be louder. Yeah, too many things changing at once. Okay, here we go. Local oscillator. Head up there. Easy to get there. So you can see the screwdriver effect now. You can see it better if you move the camera like this. The SDR has proven to be an excellent device because of the spectrum display. A little tiny, it moves it down. That's pretty good there. Okay, tune the radio a little bit. Doesn't sound very loud, but then I fooled with the volume. So there we are. So the radio is now doing its thing. Wow, something's become very microphonic. Never noticed that earlier. So we do the same thing now, only now the image is above. So the image will be at close to 31 megahertz. The radio should receive it again. So right now we're getting this at 4.5. I shouldn't have to touch that other trimmer, but I think I better. That's the best we're going to get. About 5, just a hair above 5. So now we'll compare it with the image reception, which is going to be close to 31 megahertz. Let me turn this down. Okay, I'm turning it down, so we're recalibrating. 3. 3 is the new number. There we go. So I'm trying to put this with the highest meter reading. 3 on the other, a little over 2 on this. Is that 2.7? Could be. Could be. I think that's better. I think. Okay, well, the video came to a sudden end there for me when my hard drive got jammed. So I tend to do this regularly while I'm shooting these videos. But in any case, I'm finished anyway for the day. Frankly, I'll bet you the rest of the bands are aligned properly, and really the issue was dealing with this top band anyway. So, but we'll check them out tomorrow. I'll put the radio back together. I think it'll all be done, and I think that'll be it. So thanks a lot for watching. I hope you got a kick out of that, and see what's next.